Good morning, ladies and gentlemen. For me, it is an honor to greet Professor Жерар Муру with the performance of two pieces. One is a suite of Asian dances from the Balkan area, and the other is the first and best by Doktор.
Ваше превъзходителство, драги гости, скъпи колеги, добре дошли на церемонията по връчване на доктор хонорис кауза на Българска академия на науките на професор Муру. Позволете ми съвсем накратко да ви представя професор Муру. Жерар Муру е роден на 22 юни 1944 г. в Албервил, Франция. Дисертация в университета Париж 6, Пиер Мари Кюри. След това работи в лабораторията за приложна оптика в Париж, Университета на Рочестър, Великобритания и Мичиганския университет в Съединените американски щати. Научните му интереси са в областта на лазерната оптика и физиката на електрическите полета. В Университета на Рочестър през 1977 г., заедно с тогавашната си студентка Дона Стрикланд, предлагат нов метод за генериране на свръхкъси и свръхмощни лазерни импулси. За този резултат през 2018 г. заедно с Артер Ашкин и Дона Стрикланд получават Нобелова награда по физика за фундаментални открития в областта на лазерната физика. Един от най-значимите приноси на професор Муру за развитието на лазерната физика е създаването на проекта Екстремна светлина. Проектът предвижда изграждане на няколко лазерни центъра в Европа. Благодарение на активната работа на професор Муру с Европейската комисия, проектът Екстремна светлина е признат като нова научно-изследователска инфраструктура от общо европейски интерес и е част от европейската пътна карта. С цел участието на България в изследователската фаза на този европейски проект и с активната подкрепа на професор Муру е създаден консорциум за научни организации, които са водещи в изследванията в областта на лазерната физика в България. Това са Институтът по електроника на Българска академия на науките, Институтът по физика на твърдото тяло на Българска академия на науките и Физическия факултет на Софийския университет Свети Климент Охридски. Водеща организация в този консорциум е Институтът по електроника на Българска академия на науките. Не са много световно известни учени, Нобелови лауреати, които така активно работят за включване на България и институти на Българска академия на науките в европейските научно-изследователски структури. Професор Муру е един от тях. За нас е чест днес да връчим най-високото отличие на Българска академия на науките доктор хонорис кауза на професор Муру.
От името на управителния съвет на Българската академия на науките, ние, избраните от Общото събрание на Българската академия на науките, членове на управителния съвет на Българската академия на науките, на основание член 2, алинея 2, точка 1 от Закона за БАН и във връзка с член 60 от Закона за висшето образование, по предложение на председателя на Българската академия на науките присъдихме и присъждаме на професор Жерар Муру почетното звание доктор хонорис кауза на Българската академия на науките за постижения в развитието на изследванията в областта на лазерните науки и технологии. Подписали главен научен секретар професор Евдокия Пашева, председател на Българската академия на науките академик Юлиан Ревалски.
Mr. the President of the Academy of Science, dear colleagues, professors, dear also students, dear friends, dear Her Excellence from France. Thank you very much for coming to see this ceremony. I'm thinking about a good friend of mine who died 13 years ago, Professor Solomon Saltier. And I would like to dedicate this ceremony, to him. When we came back from the United States with my wife, Marcel, after 30 years spent in the United States, the European Union was looking for very large-scale infrastructures. I proposed the idea of extreme light infrastructures, ELI ideas, and it was immediately received, extremely well. And when the European Commission asked me, where I wanted to put it, I said, I'd like to have it in France, in Paris, on the plateau of Palaiseau, near my office. I said, no, Gerard, this is not a good idea. What we lack is a beautiful infrastructure, what you are proposing, but it should be built in the emerging countries, like Bulgaria, like Romania, like Hungary, like Czechia. And I have to say that at the beginning, I didn't understand, why, But now I understand it much better. They were absolutely right to do that. And I'm very proud to have initiated this activity. Now, one of the, maybe the first country that we visited was Bulgaria. Because Bulgaria, one of scientists, very active scientists, very good scientists, Solomon Saltier, was a champion of the idea. And he wanted to have at least one part of it in Bulgaria. And so we met a number of times, and 2 times, I think, twice in Bulgaria. And a few months later, he just died without any, sign of a disease. He just died. It was amazing. And it was really a big shock, and also it was really a shock for Bulgaria because they basically lost its leaders. And I have to say that at the first conference that we had on Eli, I had my name tag was not Жерар Murу, but it was Solomon Saltier. And so I'm thinking a lot about him now. So I'm going to, of course, to give a presentation now about the reason I got the Nobel Prize with Donna Strickland. I have to say one thing is, when the Nobel Prize is announced, it's always the first Tuesday of October in physics, okay? In physics. And I was going to the swimming pool because I like I'm a swimmer. And around 12 o'clock, noontime, and my secretary ran after me and said, Gerard, you should come. Because we have this phone call from a foreign country, you should take it. So I took the phone, and it was the chairman of the Nobel Committee announcing that I was a laureate of the physics prize. And with also Art Ashkin, but he had it now. Of course, he was already of course extremely happy about this news, and he said, "But there's more to come. I have to announce that you are going to share it with your former student, Donna Strickland." And that, I just received in a few minutes interval 2 incredible news. The first, that I was nominated, I was laureate for the Nobel Prize, which was, of course, extremely important. But the other one was also maybe better because I was going to be one of the hundreds, scientists who received the Nobel Prize. But Donna was the third scientist woman to receive the Nobel Prize, behind Marie Curie and Maya Gopher-Meyer. Now we had Donna Strickland, my student. So that tells volumes, of course, about what we can, as a professor, such a distinction, means for someone like me. So that was of course extremely. It was a very, very impressive announcement for me. So, after the announcement, of course, there is a ceremony. The ceremony is, so the announcement is first Tuesday of October, and the ceremony is December 10 of December. It's always December 10 of December because it was always the anniversary of the death of Alfred Nobel. So I'm going to, you have to give a lecture. I'm going to give you a snippet of these lectures, and always, in memory of Solomon Saltier. So I guess I should have everything. So my lecture was on extreme light. So I will tell you a little bit about what is extreme light and these applications. I'm going to be very brief. Okay. So I'm starting from by my conclusions about extreme light of my lectures. And my lectures is, as I said, about extreme light, but I'm going to define it in a minute. I conclude by saying that extreme light is capable of generating the largest fields, the largest accelerations, the largest temperature and the largest pressure. It carries the best hope and opportunity for the future of science and society. And this is basically, the last sentence corresponds to the motto of Alfred Nobel, because he dedicated his life for the benefit of humankind. After this, I believe that the best is yet to come. We have done a lot in this field, but the best is yet to come. And I think now maybe I would like to do it in the future with Bulgaria.
Bravo.
Thank you. So I'm going to define extreme light a little bit. Because we developed this technique, laser technique, to produce enormous power, enormous peak power. Power which is what we call petawatt. Petawatt is 1,000 times, the world grid power. This is very respectable, of course. But what is amazing is the way we do it. This 10 to the 15 watts. In fact, we do it in a very simple manner. If you remember that power is energy divided by time, what we do with our laser, we produce a very small amount of energy, but in an extremely short time. 1,000,000 of a billionth of a second. And if you can deliver 1 joule of energy, which is a unit of energy, a very small amount of energy, in 1,000,000 of a billionth of a second, then you have 1,000 times the world grid power. And of course, this is, as I say, respectable, and we have now I have to tell you what we can do with this kind of peak power. Of course, from the inception of demonstrations of the laser by Ted Neyman in 1960, from the idea of Charles Towns, of course, which is considered as the inventors, and Ted Neyman is considered as the first who demonstrated this idea of lasers. But the laser was always dealing with what we call atomic physics. All right. Okay. Physics where the energy, the characteristic energy, is in what we call electron volt. And so this is atomic physics, molecular physics, and this kind of physics. Now, with this extreme light I just described, we will move from the EV physics, electron volt physics, from atomic physics now to the subatomic physics. Well, now the characteristic energy will be more like in mega electron volt, giga electron volt, tera electron volt, and we hope that one day peta electron volt. Okay. So this is a phenomenal jump, and this is what I like to use as an introduction. Now, just to give you an idea, I talked about TeV physics. TeV physics, you have a good example, at CERN. You heard about the Higgs boson demonstrations. It was done on the LHC, Large Hadron Collider, at CERN. The accelerators is 27 kilometers of circumference. The next one will be maybe 100 kilometers of circumference. This is really to produce the energy that is needed to go in these regimes of subatomics and particle physics and so on. And so what we can do with extreme light now, with the laser, we can compactify this kind of machines, accelerator, by huge extent, by a factor of 1,000, and hopefully maybe by a factor of 1,000,000. These accelerators, 27 kilometers, because to accelerate the particle we use microwave cavity. Now with laser Wakefield accelerator with a laser that was invented by my good friend Toshita Jima, this accelerator could be maybe set we could have about hundreds of meters, dimension, which of course is a huge leap, And now what we think we can do for the next jump, we could be not meters, 100 meters, but it could go on the finger. Okay, so you understand that is really very, very important. When we reduce the size, also we'll reduce the cost as well, usually. So that gives you just an idea what we can do with this extreme light. The other one, applications, and of course there is scientific application, fundamental physics applications. I'm just going to go more towards the societal application because I know it's usually what people like. So, as I said, now, in many fields, like medical, okay, we are using accelerators, okay, for material study. We are using accelerators for a lot of applications. We are using accelerators because they are big. So now we can really reduce the size, and now we can reduce the cost, so they can go now into hospital. And also, as I'm going to show you, we could use it, for the environment. So in a hospital, you have, if you are interested by oncology, for instance, unfortunately, for people with cancers, we have large machines, okay? And maybe the therapy of choice is considered to be the proton therapy. But to do proton therapy, you have to accelerate these particles to very large energy, like what we call giga electron volt. And almost. And the reason why proton therapy is important, as I'm going to describe it, is because you can kill only the tumors, and not the tissue before the tumors. We can also, as I mentioned, do nuclear therapy, where we are producing radionuclide and use it to. In the environment also, it is very promising, accelerator, because we could work on schemes we could produce energy but carbon-free energy, okay? Because you know that we don't know how to produce energy without destroying the planet now. we have to produce, when we produce energy, we produce carbon dioxide. Okay. So we have to find a way now to produce energy without producing carbon dioxide. And so I'm going to describe two techniques, which are, both techniques, are relying on these accelerators. So I'm going to talk about the productions of carbon-free energy, but also about transmutation of nuclear waste. Stuff which are now produced by normal nuclear power, and which are with us, can stay with us thousands of years, sometimes millions of years. So let's see. So in medicine, I'm going to repeat what I said. One beautiful application is this proton therapy, where you can focus a beam of protons, on a tumor. And if you were using electron or X-ray therapy, you could, in order to have to focus on the tumor, where the tumor is really surrounded by healthy tissue, you are going to also destroy these healthy tissues, which sits before the tumors. But with protons, it's a different thing. With proton, you can adjust the energy of your protons, so they are going to stop. All will stop at a distance, which is called the Bragg distance. So you can manage to make this Bragg distance a distance which is, just necessary. Okay, and so where you will kill the tissue, the tumors, but not the healthy tissues. So this, of course, is very important. And here again, of course, what we could use would be compact accelerators, something that you can put in an hospital. Okay. Nuclear therapy, of course, as I said, mentioned again, you can really use this. You can make produce with this accelerator radionuclides that you can use it, and you can lodge these radionuclides in the tumors, and you can kill the tumors. And of course, nuclear diagnostics, we are using a lot in the medical world, nuclear diagnostics, okay, PET scan and so on. Okay. Now, for the energy, because I think, when I got a Nobel Prize, people say, what are you going to do now? Okay, that you have a Nobel Prize. With the tone like, yeah, you got a Nobel Prize now, you can stop. Okay? No, not at all. I mean, when you have a Nobel Prize now, you have the duty to use it, to go further. And so I said what I wanted to do is to try to produce safe nuclear energy. And nuclear, of course, the energy is not well considered because the material, the element that we're using, uranium, and because the choice has been done mainly because with uranium you can make plutonium, with plutonium you can make atomic bombs. And so the choice was strongly biased toward the militaries when really the big decisions about nuclear energy were made. But there is an element which could be used instead of uranium, would be thoriums. I'm going to discuss a bit about. Now, also, point number 2, transmutations. We could transmute, right, with the fact that we can produce these particles now, high energy particles, namely neutrons, we could use it to treat nuclear waste, to transmute, you know, all this bad stuff which is produced into neutral elements. So, speaking about thorium and nuclear energy, this is a nuclear power plant, and it's typically a gigawatt power, okay, power plant. And a typical gigawatt power plant produce about 10 billion kilowatt hours a year. Okay, this kind of standard for a power plant. But to produce this 1 gigawatt power plant a year, you need 3 million tons. 3 million tons of coal. And 3 million tons of coal correspond to about 100 trains with 130 cars. Huge amount of coal. And that, of course, emits tons of carbon dioxide. If you are using atomic energy, you do better. Now, when it's based on uranium, you are talking about now only 300 tons of uranium. Now, if you are using thorium, now you only need 1 ton. Okay? And in both cases, uranium and thorium, of course, you have 0 productions of carbon dioxide. So this is something very, very important for society, you know, to reconsider, to revisit our choice of that we were made, you know, with nuclear energy. Now, once you have when you are producing this energy, nuclear energy, you are also producing bad guys, bad elements. They are called minor actinides, like neptuniums. And neptuniums have lifetimes about half-life of 2 million years. Okay, and they're a nasty element. Okay, and you have curiums, and you have plutoniums, and you have americiums. Okay, all of them have long lifetime. So we have, of course, to get rid of them right now. Especially in France. France is really a leader in nuclear energy, and what we are trying to get these products, this minor actinide. We are going to try to bury them. Okay. What we propose here is to transmute them into elements which are completely inoffensive. Okay. Here, the way we do it, if you take this nucleus of neptunium, we come with neutrons, which is produced by the laser, okay, by this compact unit, and then we are going to fission this material, these elements, and you are producing now elements which have lifetimes of minutes, days, okay, something like that. Very, very, very significantly shorter than million years. So this is one thing that we can do with lasers. This will be really something that will be very important to do, okay, because it makes nuclear energy safer. In order to use the lasers, because you need you need high peak power, you don't need only high peak power, but you need high average power as well. That means high repetition rates. You have to reinvent a laser, and this is what we are doing right now at the École Polytechnique, where you have the laser now is based on optical fibers. And why we are using optical fibers to amplify the laser, the light, is because we can cool it easily and so on. So anyway, once we have these lasers, these lasers, what we do now, we are producing these protons, and we send it in this reactor here. Okay, we are going to produce now neutrons, and these neutrons are going to do the transmutation. We'll do either the transmutation or will be used, as to activate this material. So, okay. So now I wanted also to talk about something which is very important for the survival of our society. It is the fact that it is the problems of the debris that has been put in space after the launch of every launch. We are producing debris. Since 1957, since the beginning of the space age. We have millions now of orbital debris, surrounding the Earth. You may have seen the movie Gravity, okay? And so they move. They can be very big. They can be like cubic meter, like refrigerator, okay, size, and they can be centimeters. But they all fly at 15 kilometers per second, okay, 10 times the speed, velocity of the fastest bullet. So even if they are small, they can really ruin your day, okay. So right now, we have basically launched, since the beginning of the space age, something the equivalent of 4 times an Eiffel Tower in space. Okay? 28,000 tons. So, and about half of that is circulating around us, and ready to make a disaster, on our satellites and so on. So I'm going now to show you a short clip about this debris, and it has to do with something which happened in 1997. 1997, the Chinese tried to send a missile to destroy one of our satellites. Okay, this was just a military exercise, if you want. Okay. But by doing so, they produce enormous amount. They destroy the satellite, fine, but they produce enormous amount of debris. Okay. And now we have to, now we are, we have to clean it. Okay. So, so this is the movie now, and you will see what happened when they send these missiles, the generation of these millions of debris, but also you will see the lasers that we are building. And we are going to destroy this debris. We are going to do it in a kind of indirect way. What we are going to do, when we detect the debris in space, we are going to send short pulse lasers to the debris, and we are going to ablate a little bit, ablate some part of the debris, And these ablations will produce a rocket effect which will deorbit this debris. And deorbit the debris, so the debris will go into the atmosphere and get burned in the atmosphere. So here's a movie now. Okay? No. So I guess a movie, because I get the key. We were supposed to have a movie between the two slides. So with, I'm so very, very concerned now about the stewardship of the planet. Okay. I think the scientists, as of course, have done the work. They try to enhance our quality of life and so on. But in the process, we have already now a problem. We have been too good. And so we have now really to take care of our planet. And this is a nice thing when you get the Nobel Prize. You can see people like the Pope. So we are with Donna and myself in the Pope's office. And so I was saying, what I'm going to talk about the Pope. Okay? This encyclica Laudato Si about the planet and its inhabitants. And so we worked with Donna and talking to the Pope about what we could do with our technology, with our laser, we got the Nobel Prize for, and what we could do really to save the planet. So and we told him about transmutation, we told him about the thorium, which is the element that we could use instead of uranium. And of course, we had 15 minutes where he's very smart, And he was very pleased and told us, really, if you are able to do that, of course, humanity, So, yes, I'm going to stop here. Thank you for your attention.
Let me also, on behalf of all of you, thank Professor Muru for this very interesting lecture. And now it comes a bit an informal part of our ceremony when you have the floor to raise questions to Professor Muru. He'll be pleased to answer you.
Yeah. I think you mentioned that the pulse must be chirped according to the French flag. The blue frequency component must be in the leading cage and the red frequency component must be in the trailing cage of the pulse. And but after that, the people start chirping in the opposite way, counter French flag. Do you think that there is some effect of the kind of chirping, positive or negative chirping, what concerns the generation of extremely short pulses? Because the medium has positive improved velocity dispersion.
Sure. I did all this, all the work we did with Donna that was on CPA was the basic work was done at the University of Rochester, and I developed the application later on at the University of Michigan. By the way, I see Jean-Claude Kiefer here, which has been really extremely important for the development of CPA. He was the first one to make really an experiment with CPA. I see also even Christophe here, very involved with. But anyway, just I want to answer the question now. Yeah, I mean, you can manipulate the chirp. You can have positive chirp, negative chirp. Of course, that we can do that very well. It depends if you really want to stretch the pulse or to compress it. But we know how to do that very, very well now.
Thank you so much. It was an amazing lecture. Me as a physician, we have a most important rule, primum non nocere. It means do no harm. That's why I'm very much interested. Is it possible that it may open some doors to something dangerous?
No, of course, this is, we have always this kind of thought in our mind, okay? And that's the reason why I introduced, I said, we can produce extremely high power. And when you say that, people say, well, military must be really happy about that. And I say, well, but you have no military application because the power is not, it's based on very small amount of energy.
After this presentation, do you think that one of the greatest impacts of the invention will be to make discrimination of nuclear waste? The greatest impact after this presentation, do you think that the one of the greatest impacts of the humanity in the next 10 million years will be this transmutation of nuclear waste?
As I say, you know, this is what I want to devote the rest of my life. But not only transmutation, but also maybe trying to shift, you know, from uranium to thorium, which is the thorium is much for pacific production of energy is much better. You know.
I want to say something else. Thanks to your invention, we have the pleasure at our institute to use one of the 20-second lasers that maybe is the only one in our country. So thank you for a wonderful toy we have in the laboratory.
Yeah, but I have to say one thing. You have the first, but it should not be the last.
Of course.
So, we're very much other questions?
I just wonder, you mentioned energy applications of extreme light, but you didn't mention thermonuclear fusion. Isn't that also one of the very good examples of extreme light application?
No, it's not extreme light. It's high power laser, but not extreme. The power that you are of course referring to laser fusions. Laser fusion, you use pulses which are very long, with a lot of energy. And what extreme light is pulse very, very short with small amount of energy and high power. I mean, I did the invention at the University of Rochester when in the laboratory where they were doing laser fusion, okay? And I had big problems when I came up with the CPA. We were producing, you know, petawatt pulses and so on, but with no energy. So I had a huge amount of, we had big arguments with the director of the laboratory at that time, with the best friend now, okay? Arguing, Gerard, he said, you know, I mean, your short pulse lasers has no applications. You know, it's no good, okay? I want to have pulses with long pulses for laser fusion. No, it's not applicable. There is one application you could use, I mean, we could use short pulses in laser thermonuclear fusion in the following way. You know, thermonuclear fusion is very much like an engine, you know, where you are compressing the fuel or a diesel engine, okay? You're compressing the fuel, and like a diesel engine, you know, you have a spontaneous explosion. Okay, you don't need a spark plug. engine, with explosion, you have to compress the fuel until the fuel is to a certain point, then ignited with spark plug. So we found that we could do that with thermonuclear fusion. That is, we are using a long pulse to compress the fuel, deuterium tritium fuel, compress the fuel, and when the fuel is compressed, then we can send a short pulse, and to ignite the fuel. It turns out that it doesn't work. It doesn't work, that and we tried. Okay? And it doesn't work because the short pulse, when you have the long pulse interacting with the shell of the target shell, you are producing a lot of plasma. And then the short pulse cannot penetrate with plasma. So, yeah, too bad.
So I think that we all should agree that the lecture of Professor Muru on extreme light brought really, was presented in such a way that it brought the light on the essence of his and his student discovery. And I want to once again, on behalf of you, to thank you for this very interesting lecture, and to repeat that it is an honor for Bulgarian Academy of Sciences to discern him with our Doctor Holoris Causa Award. Thank you very much for coming.